Assalamualaikum and salam sejahtera. We are still under topic 2, Introduction to Compilers. In this video, we will be talking about implementation techniques, ways we can use to develop new compilers. So first of all, why do we need to come out with these implementation techniques? Compilers development can take a very long time. So ADA, for example, took 8 years to develop. There are ways to cut down time taken to produce new compilers. We can use a portion of existing compilers, compilers that have been developed previously, or we can also use compiler generating tools such as SableCC or YACC. Before we proceed to discussion on implementation techniques, we need to revisit the definition of compiler. Compiler is essentially a translator. It must provide a translation with the same meaning as the original source. So, for example, imagine if you are a book translator and you are asked to translate Harry Potter to Malay. So, the original Harry Potter book is written in English and you are an English to Malay translator. So once you are done with your translation exercise, you will have the same Harry Potter book, but now it is written in Malay. Now let's change the parameter a little bit. What if you are an English to Korean translator? So if you are an English to Korean translator, the result of your translation would be Harry Potter written in Korean. So what is important here is translation exercise does not change the content of the book. This is still Harry Potter book in input and in output. So it doesn't, if you are an English to Malay translator, if you are translating Harry Potter, it doesn't magically becomes Hang Tuah book in Malay. No, it is still a Harry Potter book, but now it is written in Malay. Now let's bring the same scenario in compiler development. Our translator now is a compiler, so if you have as an input a calculator program written in Java, and then we put it into a Java to PC compiler, we get as output a calculator program written in PC machine language. Okay, so imagine this is PC machine language. Now I'm going to rub this equation here so that we can discuss what if the input to the compiler is another compiler. Again, the output must be semantically equivalent. So, if the input is a program that translates from Java to Sun, the output must also be a program that translates from Java to Sun. The difference is the language that this compiler is written in. So in order to compute which language it is written in, now let's take a look at this main player here, this compiler in the middle, our translator. So this compiler translates from Sun to Macintosh. So our input is a compiler written in Sun. Our compiler will translate this program from Sun language to Macintosh language. Therefore, as the output, this compiler would be written in Macintosh machine language. Now that we have understand how compiler can produce another compiler, let's talk about the first implementation technique, bootstrapping. Bootstrapping is the process of creating new compiler using the program as input to itself. So how? Imagine if you have a new computer called the CSC machine. The CPU inside the CSC machine can execute instructions such as load, move, and arithmetic operation, etc. These instructions can be activated using machine language. So for example, perhaps to load, you need to use the code 010. And then to move, you need to use the code 100. So the first program that is created for the CSC machine might be an assembler, which is written in the machine language of CSC. The assembler is a program that can translate 3-letter codes to this instruction. So it would be able to translate LOD into 010, MOV into 100, ADD into 111, and etc. So this assembler program makes it easy to train new programmers to use CSC machine, because instead of memorizing numbers, they now just have to memorize these codes. Now imagine if you want to create a high-level programming language for CSC, one that is capable of doing more complicated tasks such as if-else, while loop, etc. To write this new compiler program, you no longer have to write it in CSC machine language. This is because we already have an assembler. So we can write using assembly codes such as load, add, move, instead of 010, 100, 111, and then we can use the assembler to compile our new Java compiler for us. So let's look at this compiler input-output. We are writing a program that can translate Java instructions to CSC machine language, and we write it using assembly language. So we use the 3-letter codes such as LOD, MOV, MUL, so we do not write it in binaries. Now we use our assembler program to translate the input compiler for us. So this is our assembler program, and as a result, we get a Java compiler for CSC machine. Now let's look at this process all over again. Our compiler can translate assembly code to CSC machine code. We put as input a Java to CSC compiler program that is being written in assembly. Therefore, as the output, we will get a compiler with the same purpose or the same content as the input, but now it is written in CSC machine language. So in the previous slide, we have explained what exactly is bootstrapping. So bootstrapping is the process of using an existing compiler for that particular machine to come up with another more sophisticated and modern compiler. Now let's take a look at the type of sample question that you might have to answer. Show how Python can be bootstrapped on a Chromebook computer using a small subset of Python P1. Now a breakdown of the question. Compiler that we want at the end of the process will be placed at output. So the compiler that we want is a Python to Chromebook written in Chrome machine language. So the compiler that we used as a bootstrap is the compiler that we will use to compile, as stated in the question, is a P1 language compiler. So a P1 language is an existing compiler for this Chromebook machine. So we put it in the middle. This is the compiler that we will use as bootstrap. Therefore, with the 2 in place, we can compute that the compiler we will develop, the program that we will develop and put in input is a Python to Chrome compiler written in P1. Bootstrapping can be in multiple steps. Let's read question 2. Show how C# can be bootstrapped on a Mac computer in 2 steps, using first a small subset of C#, C, and then a larger subset, C++. C is a subset of C++. A good idea to visualize the progression of bootstrap is to draw this circle. So we have a big circle, and the final compiler that we want from this bootstrapping exercise is C#. We will be using 2 compilers. The one that is the smallest or the earliest compiler is C, and the one in the middle is C++. So draw this diagram so that it is easier for us to visualize. So from the question, we extract that C is the earliest compiler created for Mac machine. So in the first step, we need to produce C++ compiler using C as a bootstrap. So we want to produce C++ using C. So let's break down this question. What is the compiler that we want? The compiler we want as the output is a C++ compiler for Mac written in Mac machine language. The compiler that we use as bootstrap is the smaller compiler here, or the smallest compiler, which is C. Therefore, we will use a C compiler that translates to Mac written in Mac. So from this input-output equation, we can compute that the compiler we write as input is a compiler that translates from C++ to Macintosh, but it is written in C programming language. In step 1, we have successfully produced C++ compiler, a more advanced compiler than C. Now we want to produce a better and upgraded compiler, which is C#. To do that, we will use C++ that we have produced previously as the bootstrap. So from this input-output display here, we can compute that the compiler that we will write as input would be a compiler that translates from C# to Mac, but it is written in C++. So this is how we do bootstrapping in 2 different steps. For the first step, we use C to come up with C++, and for the second step, we use C++ to come out with C#. Before we talk about the second implementation technique, let's discuss one of the advantages of high-level programming language: machine independence. It means programmers who already know a high-level language can do codings in multiple machines. So for example, if you know Java, you can develop programs using Java on Macintosh, Windows, and Linux computers. Because Java compilers for these machines already exist, you do not need to learn the machine languages of these 3 computers to write programs for them. However, if you have new computers being introduced, we need to develop new compilers for these new computers. Therefore, in order to cut down the time taken, we can use a shortcut. We can use cross-compiling technique, which is a method of reusing compiler of the same language of computers that already exist. Let's take a deeper look at the cross-compiling implementation technique. So imagine if you have a new machine, and this new machine is called Google Pixel. You want to develop application for Google Pixel, programs that can run on this machine, but you face some problems. First of all, you want to write your code in Java. Java is a programming language that you know. Second, you do not want to write in machine language of Google Pixel. However, currently, because it is a new machine, we do not have any compiler yet. And third, Java compiler for Google Pixel doesn't exist. So what we can do is we can use an existing Java compiler for any machine. So for example, if you have a Java compiler for PC, we can use some portion of this existing compiler to compile a new compiler for us, to compile a Java for Google Pixel compiler for us. So how can we use an existing compiler to come up with new compiler for the new machine? So let's break down what we know. What is compiler that we already have? We already have a Java compiler for PC. This is the compiler that we will place here, so that it can help compile a new compiler for us. So what is the compiler we write as input? We know that we want a Java compiler for Pixel. And since we will be using this compiler in the middle, it must be written in the language it can translate from. So it will be written in Java. So the compiler that we write as input is Java to Pixel written in Java. And to recap, what exactly is the compiler that we want? We want a compiler that can translate from Java to Pixel, and it can run on Pixel. So this is the final compiler that we want. Now, let's place the compiler that we already have inside the compiler section. Put the compiler that we write as input. Based on our understanding of this input-output process, what should we get as output? So the one that we get as output would be compiler that translate from Java to Pixel. Since it must have the same content with the input, the output must be the same. And it is written in, so this input is written in Java. This compiler translates from Java to PC. Therefore, this program must be written in PC. Is this the compiler or the final compiler that we want? No, this is not yet the compiler that we want, which means there is another step that we need to take. In step 1, we produce this compiler. We were able to produce the compiler. However, this is not yet the compiler that we want, which means we need to do another step. So in step 2, the output of step 1 becomes the compiler that compiles our input. So let's place our output of step 1 to be the compiler of step 2. Meanwhile, the input of step 2 would be the same input that we have written in step 1. So this is the same compiler. You do not need to write any new program. And then in step 2, by using the compiler that we have generated in step 1 as the compiler, we would be able to get a compiler that translates from Java to Pixel, which is the same content of the input. However, this particular compiler will be written in Pixel machine language, which is exactly the compiler that we want for the new machine. Cross-compiling implementation technique basically produces compiler that can provide the output in a machine language different than the one it is written in. It is a process, like we have shown previously, that involves 2 steps. Now let's take a look at question 1. A new device, Oculus Rift, is created, show how you can develop a C# compiler for this device without writing it completely in machine or assembly language if you already have a C# compiler for Android. So now let's break down this question. What is the compiler that we already have? So we already have a C# compiler for Android written in Android. So this is the compiler that we already have. What is the compiler that we write as input? So we want a C# compiler for Oculus Rift. So we want a C# compiler for Oculus Rift, and this will be written in C#. And what is the compiler that we want? The compiler that we want is C# to Oculus Rift written in Oculus Rift. So in step 1, we place the compiler that we already have inside the compiler part, and the compiler that we have written, put it into input, and we get as the output a compiler that translates from C# to Oculus Rift. However, it is written in Android. So this is our cross compiler, the output of step 1. So this cross compiler will then be the compiler in the second step of our cross-compiling implementation technique. So the input would still be the same input as step 1, and now we would be able to compute the output of this process would be a C# compiler for Oculus written in Oculus, which is the final compiler that we want. The third and final implementation technique that we will discuss is called compiling to intermediate form. So what exactly is intermediate form? It is a language somewhere between high-level language and machine language. So for example, a stream of atoms. So imagine if you have 4 computers, a PC, Macintosh, Sun, and Linux. And then we also have 4 different programming languages, PHP, Java, C++, and Perl. Now, you want the compilers of all programming languages for all the computers. So usually, this would mean developing all these separate compilers for all these separate computers, which means we need to develop 16 different compilers. However, if we decide to create a compiler that translates from PHP to Atoms, and then from Atoms to PC, then from Java to Atoms, and then from Atoms to Macintosh, and then from C++ to Atoms, and Atoms to Sun, from Perl to Atoms, and Atoms to Linux. So you can have a compilation of languages for all of these machines without having to develop 16 different compilers, as long as you are using these 2 compilers together. So for example, if you want to compile from Java to Macintosh, so you would use the Java to Atom compiler and Atom to Macintosh compiler. By using this way, you only have to develop in total just 8 different compilers, much fewer than the 16 different compilers in the previous scenario. So essentially, in topic 2, we have discussed the 3 things. First of all, what is a compiler? Compiler is essentially a translator, and a translator that provides a semantically equivalent translation. So if you are translating a calculator program, the output would be also another calculator program, just in a different language. Okay, and then we have also discussed the phases of a compiler. So we have 3 phases. So we have lexical analysis, we have syntax analysis, and then we have code generation. And finally, in this video, we've discussed the 3 implementation techniques. The first one is bootstrapping. The second one is cross-compiling. and the third one is compiling to intermediate form. And so that's the end of topic 2. We have taken a bird's eye view of the whole compilation process.